Hello and welcome to the course Design Borefields with Confidence. This is the second chapter of the third part, where we'll be taking a look at the more advanced, the more state-of-the-art methods that are implemented into GHG2 Cloud. Now, today we will be talking about variable fluid properties. Now, perhaps you recall if you made your first GHG2 simulation last month that you had to turn off the specific setting, namely use temperature dependent fluid properties. You had to set it to no, because that's the traditional way of simulating borefield that's used by a lot of software. But in GHG2 we implemented a new, more accurate mathematical model, a more accurate way of taking into account fluid properties that will have a very significant impact on how your geothermal system is designed, specifically when you're having quite a lot of cooling load. So let us get started by explaining the fluid properties. Now, here on this slide, you can see two of the four important fluid properties, namely density and viscosity. And what you can see is that the density, the viscosity, and in the next slide, the thermal conductivity, as well as your heat capacity, they are not constant because they change over temperature. And you can see that in the case of density, it's more or less constant. And we show this for water as well as three different types of antifreeze mixtures, namely monopropylene glycol, monoethylene glycol, as well as ethanol and water. Now, what you can see here is that the density of water, it's around 1000 kilograms per cubic meter. We all know that. If you go to monoethylene glycol and monopropylene glycol, we have higher densities, and a mixture with ethanol is actually has a lower density. Where it's more or less constant, especially for water, for the other ones, the density decreases when our temperature increases. Now, just to note, you can see that we have different percentages of antifreeze. That's because all antifreezes have a different freeze protection, so we made sure that we selected the percentage of antifreeze mixture such that they have the same freezing point to make the comparison quite fair. So that's one thing. The other thing, which is way more significant, is that the viscosity of a fluid, it changes by a factor of 3 in some cases. So here you can see again that water has actually the lowest viscosity. It changes not so much, but all our other mixtures, especially our monopropylene glycol mixture, it goes from a dynamic viscosity of around 8 millipascal per second to around 2 millipascal per second. So that's a factor 4 of difference when we go from temperatures of -5, which are more or less the lowest temperatures you will get in your geothermal simulation, to temperatures of 25. So that's a very significant drop there in viscosity, which is also, the same for all other fluids. Now, why do we care about these fluid properties? Before we talk about that, just the same story here for the conductivity and the heat capacity. Here the story is a little bit different, because what you can see is that if you, for example, look at the solid lines at the conductivity, they increase when temperature, so the heat transfer becomes better with higher temperatures. And also here water is quite significantly above all the other lines. And when we talk about heat capacity, all heat capacities also increase when our temperatures increase, except for water and ethanol mixtures, there is a slight decrease. Now, of course, we do not care about fluid properties themselves, but these fluid properties, they are used to calculate the Reynolds number. Perhaps you recall the Reynolds number, it told us something about the flow regime, whether we're laminar or turbulent, and it was a really, really important parameter when we talked about the effective borehole thermal resistance. So if we now take all these different lines into account and we calculate how the borehole resistance or the Reynolds number changes with temperature, we get this graph. And this is really interesting because, again, you can see that water is always at a way higher Reynolds number, and because of the low viscosity, it gets into a turbulent state way sooner. But the other lines, which is interesting to note, is that they change from, let's again take monopropylene glycol, the worst kit in class as an example. It's 1000 at -5 in this case. This was, by the way, for a single DN40 probe, and it goes up to 3500 for 25 degrees. So in this temperature range, from -5 to 25 degrees in this case, we will cross the limit from laminar to turbulent flow. And for all other fluids, we also will cross that, but at a different temperature. And this is interesting because if we now look at the figure we're actually interested in, namely the fluid properties and its relationship to the borehole resistance, we see here that depending on the temperature of your fluids, for exactly the same probe, exactly the same flow rate, just changing the temperature and the fluid properties, you will transition to turbulence somewhere at a certain temperature. And what you can see is for water is always turbulent, but for monoethylene glycol, which has the lowest viscosity, you will see that already at, let's say, 1 degrees in this particular flow rate, this particular probe, you will transition to a turbulent flow rate. But for ethanol and monopropylene glycol, this transition will occur at 10 or at 15 degrees. But the interesting thing is that your borefield simulation, your temperatures typically vary quite a lot. You can easily have temperatures in winter of around 0 degrees and in summer around 15 degrees. So, of course, when you're switching from heating to cooling and your temperatures and your borefield fluctuate, also you will move in and out of turbulence quite often. And this is something that has not been taken into account over the last decades. And that's why in GHG tool we now added this explicitly. So we're going to calculate for you the fluid properties every month of every hour, as well as the borehole resistance. And as we will show you now in GHG tool Cloud, this can have quite a significant effect on how you design geothermal borefields and also can avoid you oversizing them tremendously. So here we are in GHG tool Cloud, and as you can see, I created 2 cases for you to illustrate how this setting or this newer, more accurate model can help you design better borefields. So just to start, as we had in the last chapter of the second part, we don't use any temperature-dependent fluid properties for the moment. Now, again, if you want to create this example yourself, all the information is over at the bottom of the chapter over on our website. We have a borefield of a line of 6 boreholes of 110 meters, a borehole resistance 30 volume percent of monopropylene glycol with a certain flow rate, and we have a thermal demand with a significant imbalance here and a certain cooling demand. But let us just simulate the results, and what you can see here is that we have a borefield which is, again, as is often the case in our climate region, limited by the maximum temperature. So we're here even above it, 17.3 degrees, and we are quite high above our temperature threshold of 0 degrees or minimum limit. So traditionally you would say, okay, this borefield is well designed. You can argue that 17.3 is actually good, or that it should be slightly deeper, the boreholes, in order to make sure that we are close to the 17 degrees. But let's not go into detail about that philosophical discussion in this case. You could argue this is a good design. We need 6 boreholes of 110 meters. But what you can see here is we have a Reynolds number. It was all laminar. But by default, and so as was the historical assumption, the Reynolds number is calculated based on the minimum temperature limits, which is 0 degrees in this case. But during injection, during cooling, we actually are way higher. So chances are that due to the change in our viscosity and so forth, we actually have a transient state and our heat transfer is actually better. So what we can do is we can go to duplicate scenario, let's call it case 2 with variable fluid properties. And the only thing we are going to change is we go to general here and we say, okay, let's work with some temperature dependent fluid properties here. And let us go ahead and simulate it. So we didn't change anything, we just say, okay, use a more accurate model. And indeed, you can see that during injection, we have now a transient flow rate. And we are not anymore at 17, but the reality is that just by using a more accurate model that actually calculates the Reynolds number and the borehole resistance at every instant, we now have temperatures closer to 16 than to 17. So basically our borefield is oversized. We do not need 6 boreholes in order to cope with our limits. You can also see here that our effective borehole resistance is actually significantly lower than our 0.23 we had during extraction. So let us go ahead and duplicate this and see fewer boreholes to see how many boreholes we can cut, because let us, for example, go to 5 instead of 6. And let us play around to see how many boreholes we can actually get rid of due to this more accurate assumption. So here we see that we are at 16.7 degrees Celsius. So we're still below our 17 degrees, and we already cut away 1/6 of our original design. You can also see that we are now even higher. We have now an even higher flow rate. And that's because, as we had here, our flow rate was given for the entire borefield. So by going from 6 to 5 boreholes, our flow rate also increases, making it also more turbulent, which is even more interesting. Let us just check if we can go down to 4 boreholes instead of 6. And so cut away one third of the system. And yeah, it now becomes a little bit more difficult. We're now at 17.83 degrees Celsius, which is probably too high. But you can see that it's somewhere between 4 and 5 boreholes, perhaps 4 and a little bit deeper. You can play around with that yourself. But just to showcase that just by changing this one simple assumption, you can get way more accurate results, especially when you're having quite a high cooling load. And I've seen projects where this can change the design with 20% easily of your system. So it's a really important assumption, a really important improvement in how you can make more accurate geothermal borefields. And that's also why by default this setting is on. Now, just having temperature dependent fluid properties can also give you another interesting phenomenon. So let's go to case 2, where we calculate the required borehole depth. We'll come back to that later in this course. But if we jump to our results step, we have a temperature profile like this, which looks extremely strange at first sight. And so we have our downward going temperatures here, and then suddenly there is a drop. Now, why is that? Now, I said our fluid properties are calculated at every instance, at every month during heating, cooling, and for an hourly simulation at every hour. So what we see here is that, okay, our fluid properties are temperature dependent. We see here that our minimum Reynolds number is laminar. It will be this situation here. But what we see is that in these first years, during peak extraction, we are at 4 degrees, 2 degrees, and our flow rate still is transient. But after a certain amount of years, due to the imbalance, our temperatures go down and we do not enter anymore this turbulent flow rate. So we can see this sudden drop because we now have a way more accurate model to take into account this varying in Reynolds number and borehole resistance. So in our previous assumption, you would just have this low borehole resistance during the whole simulation period, and this phenomenon would go unnoticed for you. But now you can clearly see, okay, the first years are rather good, but then there is a sudden drop in efficiency, and you can try to change your design in such a way that you can overcome this problem and make the efficiency better overall. And that's an interesting exercise to do for yourself. So these are two cases to illustrate the importance of using variable fluid properties. It's a no-brainer, basically, but I just wanted to inform you that this is, when you compare it to other simulation software, a significant improvement that you should use for all your designs, basically. Now, in the next chapter, we will go even further, and we will not talk anymore about variable fluid properties, but also the flow rate is no longer constant, and also this will have a tremendous effect on the way how you design bore fields.